Hello friends, how are you? Today we are going to complete the real numbers chapters. In last video we have seen the real numbers chapters up to some part. Up to introduction and fundamental theorem of arithmetic and what is the proof for theorem, the LCM, HCM and related problems and examples, everything we have seen in last class. In this class we are going to see revisiting of irrational numbers, and in that we have two theorems are there. Theorem 1.2, that is, if p is a prime number, if p divides a square, then p divides a also, where a is a positive integer. If any number a square, a is there which is a positive integer and p is the prime number, if p divides a square, then p divides a also. That is one theorem. We will see the proof with example. And second theorem is prove that root 2 is irrational. Okay, what is the irrationality of root 2? That with proof we will see, and related examples and problems also we will explain here clearly. Okay, let's go to the part. So, we are revisiting the irrational numbers is the concept today. Here recall a number S is called irrational if it cannot be written in the form of p by q, where p, q are integers and q is not equal to 0. So, what is rational numbers? Rational number is nothing but the numbers which are written in the form of p by q, where q is not equal to 0. Okay, these are rational numbers. And what are irrational numbers? The numbers which cannot be written in the form of p by q are called the irrational numbers. That means it is not possible to write that numbers in the form of p by q, where q is not equal to 0. Some examples of irrational numbers are root 2, root 3, root 5, root 15 and pi 0.100. That means these are numbers, never ending numbers. The digits go on continuing like this. So it cannot be represented in the form of p by q. Such numbers are called irrational numbers. Okay. In general, root p is called irrational if p is a prime number. Suppose in the root any prime number is there. That means root 2, where 2 is a prime number, root 3, where 3 is a prime number, root 5, where 5 is a prime number, root 11, where 11 is a prime number. Like that, if any prime number is there in the root, then such number is called irrational numbers. Other than that, root 5 into root 3, like this. This also we call it as, that is root 15. This types of numbers also we called as irrational numbers. Like that, if in general, if p is a prime number, then root p is nothing but the irrational numbers. So here we will see the theorem. What is that theorem says? Let p be the prime number, and if p divides a square, then p divides a. If p divides a square, then p divides a, where a is a positive integer. Okay, so if we take any positive integer a, then a square is divided by p. Okay, a square is divided by p, then a also divided by p. Okay, if a square divides p, then a also divides p. This is the theorem. Okay, here let's see with the proof how it is possible. Let the prime factorization of a be as follows. Since a is given a positive integer, any positive integer can be written as factorization of prime numbers. Whether it is a composite number or a prime number, we can do the prime factorization. If it is a prime number, then it has only one and the same number as prime factors. If it is a composite number, we can represent with other prime numbers also. So here what it has written, A is equal to P1 into P2 and so on Pn, where P1, P2, Pn are the primes. So here A is a positive integer, it can be represented as multiplication of prime numbers. Okay. Here P1, P2 and so on Pn are primes and they are not necessarily distinct. That means sometimes P1 is equal to P2 and so on. Equal numbers also will be there. So any positive number A can be represented like this. And we take A square. A square is nothing but multiplication of A into A. Here one A is P1, P2 and so on Pn, and another A is P1, P2 and so on Pn. By multiplying these two, we will get P1 square, P2 square and so on Pn square. Okay. So A square we got P1 square, P2 square and so on Pn square. Now we are given P divides A square. Okay. Please listen carefully here. P divides A square. So this whole thing is divided by P. A square is nothing but P1 square, P2 square and so on Pn square. If P divides A square means this whole thing is divided by P. Therefore, from the fundamental theorem of arithmetic, it follows that P is one of the prime factors of A square. Okay. So what it says, if P is divisible by, see here, if P is divisible by A square, then and P is a prime number, that is nothing but P is one of the prime factors of A square. Okay. This is from the fundamental theorem of the arithmetic. So however, using the uniqueness part of the fundamental theorem of arithmetic, we realize that only prime factors of A square are P1, P2 and so on Pn. So what this equation says, let this equation be 1. What this one equation says, what are the prime factors of A square? Whether it is P1, P2 and so on Pn. Other than this, no prime factors exist. Other than this P1 to Pn, no other prime factors exist. That is the uniqueness of the fundamental theorem that we have seen in the last class. So the only prime factors of A square are P1, P2 and so on Pn. And here what given, P divides A square. That means A square is divided by P. So what is the possibility? If P is a prime number, then P is nothing but one of these P1, P2 and so on Pn. Okay. So here we have two concepts are there. First, he is taken A square is equal to P1 square, P2 square and so on Pn square. All these are the prime numbers. From the fundamental theorem of arithmetic, what it says that no other prime factor exists for the A square. The prime factor should be P1, P2 and so on Pn. Okay, these are the only prime factors for A square. And from the theorem definition, what it says, P divides A square where P is a prime number. So if P is a prime number and it divides A square, and A square is having only prime factors of P1 to Pn, that means P is nothing but one of the P1, P2 and so on Pn. Okay. So now since A is equal to P1, P2 and so on Pn, P divides A. So what we got here, A square is equal to P1 square, P2 square and so on Pn square. This is equation 1. And A square is divisible by P is a prime number. Suppose this is equation 2, right? So from these two equations, what we conclude here, A square is equal to P1 square, P2 square and Pn square. From the fundamental theorem, what we conclude? A square is having only prime factors of P1, P2 and so on Pn. And from the definition we see that A is divisible by P, which is a prime number. So what is the possibility? P is one of P1, P2, P3 and so on Pn. So P must be one of the prime numbers of this. Then only these two conditions are true. This is from the fundamental theorem of arithmetic and this is from the definition. So the possibility is P one of the factors of P1, P2 and P3 and so on Pn. So P must be one of these things. Since A is equal to P1 into P2 and so on Pn, here P is one of these factors. So A is divisible by P. Understood, no? So what he is saying, P is one of these factors and A is equal to P1, P2 and so on Pn. So if P is one of these factors, then P is multiplied by P, A is divisible by P. This is the theorem. Okay, understood, no? Here I will explain with one example. Let's say some 60 is our A. What are the prime factors for 60? 2 into 2 into 3 into 5 are the prime factors for A. That means this is P1, P2, P3, P4. And what is A square? A square is equal to 2 into 2 into 3 into 5. This is 1A. Another A is 2 into 2 into 3 into 5. Okay. And let us assume that P is another prime number which is divisible A square. Here P is a prime number. So if P is a prime number and A square is having prime factors like this, from the uniqueness of the theorem, no other prime factor exists for A square other than 2, 3, 5. 2, 3, 5 are the only prime factors for A square. So what is the possibility for P? Possibility for P is P can be 2 or P can be 3 or P can be 5. Since P is a prime number and A square is having prime factors of 2, 3, 5, the only possibility for P is 2, 3, 5. No other possibility exists. So, So, P can be 2, 3 or 5. So, from A what we got? 2 into 3 into 5. So, since P can be 2 or 3 or 5, so here A prime factors also 2, 3, 5. That means A is divisible by P. Okay. So from this what we got? P can be 2, 3 or 5 and we know that A is nothing but having A is having prime factors of 2, 3, 5 only. So from this A is divisible by P. Okay. Understood, no? So once again you see it clearly, then you know the concept correctly. Okay, this is the first theorem, that is if P is a prime number and P divides A square, then P divides A, where A is a positive integer. Next, theorem 2, the second theorem in the irrational numbers is root 2 is a irrational. Here root 2 is a irrational. In general concept, what we know, anything, any prime number under root is a irrational number. So here 2 is a prime number, so root 2 is a irrational number. Now we will prove how root 2 is a irrational number. This proof is based on a technique called proof by contradiction. What is proof by contradiction? First we will take the contradiction statement to the given statement. That means if root 2 is a irrational number is the statement given in the problem. We assume that root 2 is a rational number, and by assuming root 2 is a rational number, we will do the calculations and we will get the wrong results or contradictory results. So we can conclude that because of our assumption root 2 is a rational number, we got these contradictory conclusions. So it means our assumption is wrong. That means root 2 is a irrational number. Okay, that is the proof by contradiction method. How it is possible, that we will see. So here by observing, we assume to the contrary that root 2 is a rational number. What is the given statement? Root 2 is a irrational number. So contradictory statement is root 2 is a rational number. We take root 2 as the rational number. So if root 2 is a rational number, then there exist an integers r and s, where s is not equal to 0, such that root 2 is equal to r by s. How this statement came? What is nothing but rational number? Rational number is nothing but a number which is written in the form of p by q, where q is not equal to 0. So if a number written in the form of p by q, where q is not equal to 0, then this is called as a rational number. So here we assumed that root 2 is a rational number. It can be written as root 2 is equal to r by s, where s is not equal to 0. R by s or p by q, same, only in this representation changes. R by s where s is not equal to 0, or p by q where q is not equal to 0, both are same. So root 2 is a rational number by assumption, so it can be written as r by s where s is not equal to 0. Suppose if r and s are having any common factor other than 1, then we divide by the common factor, so that root 2 is equal to a by b, where a, b are the co-prime. Okay, that means suppose if r by s is like this, r by s is equal to some 3 by 9, like this it is there. Here 3 and 9 both are having common factor of 3, okay, and 1 and 3 are common factors for 3, 9. So here 3 by 9 we can divide it with 3, then we get 1 by 3. So here this 1 by 3 is having common factor as 1. Same thing here it is saying. If r and s are any other common factor other than 1, then simply we divide with the common factor. Here 3 is the common factor, means we divide with 3, so that we can get 1 by 3. 1 and 3 are having common factors of 1 only. So such type of numbers are called co-prime numbers. That means the numbers having common factors 2, 3, 2, 5. All these numbers are having common factor as 1. Common factor 1, common factor 1. This type of numbers are called co-prime numbers. So by assumption root 2 is a rational number, and we have written in the form of root 2 is equal to r by s, where s is not equal to 0. If r and s are having any common factor other than 1, we divide both r and s by that common factor, and we have got the result root 2 is equal to a by b, where a and b are the co-prime. Okay, that means both are having only 1 as common factor. So from this equation root 2 is equal to a by b, what we got, a is equal to root 2 into b. Okay, a is equal to b, if you go that side it becomes a is equal to root 2 into b. So on squaring of this both sides we got 2b square is equal to a square, 2 into b square is equal to a square. Here therefore 2 divides a square. Okay, here b square is equal to a square by 2. Okay, since b is an integer, b square also integer, that means a square is perfectly divisible by 2, then only we will get this integer. So a square is divided by 2, that means 2 divides a square. Now from the theorem of 1.2, what is the previous theorem says? If any prime number is divides a square, then the prime number divides a. So here 2 is a prime number which divides a square, that means 2 divides a from the theorem. Okay, so here 2 divides a means a can be written as 2 into c. Okay, understood now? Here 2 divides a means we can represent a as 2 into c, where c is some integer, that means c is equal to a by 2. So 2 divides a, we will get some integer, that means we can written as a is equal to 2c. So I have written like that, a is equal to 2c. By substituting this equation 2b square is equal to, instead of a I have given 2c. So we got 2b square is equal to a square, 2b square is equal to, instead of a I got 2c whole square. So 2b square is equal to, 2 square means 4c square. Okay, here we got 2b square is equal to 4c square. So from this 2 1s are 2, 2 2s are 4, we got b square is equal to 2c square, that means 2 divides b. So from this what we got, c square is equal to b square by 2. From this what we got, c square is equal to b square by 2. So here c is an integer, if it is integer means b square is perfectly divisible by 2, b square is perfectly divisible by 2. So from the same theorem, if 2 divides b square, so 2 divides b. This is also from the previous theorem. If any prime number divides b square, the same number p divides b. This is also from the theorem. So here we got 2 equations. First one is 2 divides a, this one. Next one is 2 divides b. 2 divides a and 2 divides b means a and b both are having 2 as common prime factor. So here what we got, therefore a and b have at least 2 as common prime factor. But this contradicts the fact that a and b have no common factors other than 1. Okay, here what we got from the assumption a and b, from the assumption we got a and b are co-prime, that means no other common factor exists other than 1 for a and b. And here from the explanation what we got, a and b having another common factor which is 2. So our assumption is they are co-prime, but we got there is other common factor 2 for a and b which says that they are not co-prime. So by assumption we got a and b are co-prime, but by explanation we got a and b are not co-prime. This is the contradiction statements. These two are contradiction statements. So this contradiction has arisen because of our incorrect assumption, so that we conclude that root 2 is a irrational. Okay. So how this contradiction came? By taking root 2 as rational, if we process that statement, then we got two contradictory statements, that is a and b are co-prime and a and b are not co-prime. So our assumption is wrong. That means root 2 is the irrational number. Okay, understood now? You please see once again, then you will get the clear cut idea. Okay, here root 2 is a irrational. Similarly, we go for root 3 also. Okay, this is the example. Here root 3 is a irrational. First we take root 3 as rational. That is proof of contradiction. If root 3 is rational means root 3 is equal to a by b or p by q. Anything we can take. Here I will take p by q. Root 3 is equal to p by q, where q is not equal to 0. So squaring on both sides we get root 3 whole square means 3 is equal to p by q. So p square by q square. So p square is equal to p square is equal to 3 into p square is equal to 3 into q square. So here since p and q are integers, so we write q square is equal to p square by 3. So p square is divisible by 3. So here p square is divisible by 3 and 3 is a prime number. So p is divisible by 3. This is from the theorem, first theorem. Similarly, so if p is divisible by 3, let us assume this statement as 1. Then what we got, if p is divisible by 3, then p can be written as 3 into c. So we substitute this equation in the above one, p square is equal to 3 into q square, p means 3 into c whole square is equal to 3 into q square. So 9c square is equal to 3 into q square. Here what we got, c square is equal to 3 ones, 3 threes. So this 3 go here, it will come in the denominator. So here c square is equal to q square by 3. Since c is an integer is equal to q square by 3, then q square is perfectly divisible by 3. So q square is divisible by q square is divisible by 3 means from the theorem what we got, q square is divisible by 3 and 3 is a prime number. So q is divisible by 3. This is equation 2. But due to our assumption, here root 3 can be written as p by q, where pq are co-prime. Co-prime means other than 1, no prime factor exists for this. So here this assumption, same thing we got here, pq are co-primes. And from these equations 1 and 2, we got p is divisible by 3 and q is divisible by 3. That means p and q both are having 3 as a common factor. So on one statement we got p and q are co-prime, which means other than 1 no common factor exists. In other statement we got 3 as another common factor. These two are contradictory. So these statements 1, 2 and our assumption are contradictory. So why this contradictory came? Because of our assumption root 3 is a rational number, which is wrong. That's why we conclude that root 3 is a irrational number. Same thing here. Here root 3 is a irrational number. Let us assume to the contrary, root 3 is a rational number. If root 3 is a rational number, root 3 is equal to a by b, where b is not equal to 0. We have written in this form. So root 3 is equal to a by b, and b into root 3 is equal to a. Squaring on both sides, we get 3b square is equal to a square. So here b square is equal to a square by 3. B is an integer, so b square is equal to a square by 3 means a square is divisible by 3. So from the theorem, a is also divisible by 3. This is the equation 1. So we can write if a is divisible by 3 means a is equal to some constant into c, that is 3 into c for some integers. By substituting a value in this equation, we got 3b square is equal to 9c square. So b square is equal to 3c square, c square is equal to b square by 3. Since c is an integer which is equal to b square by 3, this b square is completely divisible by 3. So from the theorem we got b is divisible. If b square is divisible by 3 and 3 is a prime number, we got b is divisible by 3. So from 1 and 2 we got a and b are divisible by 3. But we assumed that a and b are co-prime. Okay, a and b are co-prime we assumed, which means no other common factor exists for a comma b. But here we have a comma b common factor as 3. This contradiction arises because of our incorrect assumption that root 3 is a rational number. So root 3 is a rational number. Okay, understood? By practice you can easily get. Okay, here remember these statements. The sum or difference of a rational number and an irrational number is irrational, and the product and coefficient of a non-zero rational number and irrational number are irrational numbers. That means here one rational number and one irrational number. Suppose 2 is a rational number and root 3 is a irrational number. Okay, then if one is rational and one is irrational, their sum or their difference, both are irrational. If one number is rational and one number is irrational, their sum and difference both are irrational. Similarly, 2 by 3 and 2 root 3, their product and division, these two also irrational. If any one thing is a rational and one thing is irrational, means their sum, subtraction or difference and their multiplication or division, all are irrational number. That is one rational, one irrational means the combination is always irrational. Okay, so here we can see it by an example. Root 5 minus 3 is an irrational. Show that root 5 minus 3 is an irrational. This is also we prove by proof of contradiction. We take root 5 minus 3 is a rational. That means root 5 minus 3 can be written as a by b, where b is not equal to 0 and a comma b are co-prime. Okay, so from this we take root 5 is equal to a by 3 plus b, plus 3, which is equal to a plus 3b by b. So root 5 is equal to a plus 3b by b. Here a and b are integers. A and b are integers. So any combination of a and b is nothing but a rational number. So this total factor, it is a rational number. You take any number. For substitute a is equal to 1, b is equal to 2, or a is equal to 3, b is equal to 4. Any integer you substitute. Minus also you can substitute. Negative integers also you can substitute. Always this thing becomes a rational number. Okay. So, and root 5 is a irrational number. Irrational number. So what we got from one side, this RHS side, we got a rational number, and from the LHS side, root 5, which is nothing but a irrational number. Okay. So this cannot be true, because one side we got a rational number and another side we got a irrational number. This is not possible. This is a contradictory thing. How this contradictory exists? This contradictory exists because of our wrong assumption. Our wrong assumption that root 5 minus 3 is a rational. This implies root 5 minus 3 is irrational. Okay, understood, no? So what we have done, first root 5 minus 3 is a irrational number. For solution, what we have done, on contradictory assumption, we take root 5 minus 3 as a rational number. Rational number means that can be written in the form of a by b, where b is not equal to 0 and a, b are co-primes. And we take this root part as separate from the equation. Root 5 is equal to a by b plus 3, that is a plus 3b by b. Since a and b are any integers, what we got, a plus 3b by b is always a rational number. For any integer, the combination of integers always give a rational numbers. So a plus 3b by b is a rational number. But here this root thing, root under prime under root, that is 5 is a prime number under root. It is nothing but a irrational number. So on the LHS side we have root 5, which is a rational number, and RHS side we have a combination of integers which is a rational number. So this cannot be true. One side it is a rational number and one side it is a irrational number. This cannot be true. This is a contradictory. This contradictory exists because of our wrong assumption. So what we have assumed, root 5 minus 3 is a rational number. Because of this wrong assumption, we got this contradiction. So our assumption is wrong. That means root 5 minus 3 is a irrational number. Okay, same thing here. Let us assume 5 minus root 3 is a rational. So 5 minus root 3 is equal to a by b. So 5 minus a by root 3. So it is so by taking the one side we got the rational number and other side we got the irrational number. So here 5 minus, not root 5 minus 3, I have taken 5 minus root 3. So for both are same proof only. Okay. Next example, 3 root 2 is a irrational number. So here solution, 3 root 2 is a irrational number. What is the first statement? Assume 3 root 2 is a rational, which is a contradictory. So we take 3 root 2 is equal to a by b, where b is not equal to 0 and a, b are co-prime. So here 3 root 2 is equal to a by b, root 2 is equal to a by b. So here also root part you take, you keep in LHS side, remaining all things you move to RHS side. A is equal to 3 by b. Since a comma b are integers, the combination of integers a by 3b is a rational number. And here root 2 is a rational number, prime under root. So here on LHS side we have a rational number, on RHS side we have a rational number. So this is the contradictory. So this contradictory arisen, due to our wrong assumption or incorrect assumption that t root 2 is a rational. So t root 2 is irrational. So all these type of problems we follow the same. First we take the assumption that the given number is a rational number, and we do the calculations such that keep all root parts in the left hand side and move all other parts in the right hand side. Since on right hand side we have all other things which is having integers only, the combination of integers, that is plus, minus, multiplication or division of integers, you get a rational number. Since on the LHS side we have root part which is a rational number, on the RHS side we have a this integer part which is a rational number. We will get the contradictory statements in both sides, LHS and RHS. So this contradictory arises due to the incorrect assumption of given number is a rational number. So we conclude that 3 root 2 is a, or given number is a irrational number. All are having same proofs. So see here, 3 root 2 is a rational. First assume 3 root 2 as rational and root 2 is equal to a by 3b. Since a by 3b are integers, a by 3b is a rational number. So but root 2 is a irrational number. So this contradiction arises due to the fact our assumption that 3 root 2 is a rational number. So 3 root 2 is a irrational number. Next prove that root 5 is a irrational number. This is same proof as root 2 and root 3. Here root 3 proof is there, no, and root 2 proof also there. Here root 2 proof also there. Same thing, instead of 2 you write 5. Prove that root 5 is a irrational number. This is the proof. Let us assume to the contrary root 5 is a rational number. So we can find integers a comma b such that b is not equal to 0. So root 3 is equal to root 5 is equal to a by b. So from that we got b into root 5 is equal to a, squaring on both sides, 5b square is equal to a square. B square is equal to a square by 5. Here a square is divisible by 5. So from the theorem what we got, a is also divisible by 5. Similarly a is equal to 5c. Since a is divisible by 5, we written as a is equal to 5c. By substituting 5b square is equal to 5c whole square. So from this we got c square is equal to b by 5. So here b square also divisible by 5. From the theorem we got b is divisible by 5. So from 1 and 2 we got a comma b divisible by 5. But as per assumption we got a and b are co-prime, which is having 1 as the only common factor. So this is the contradictory assumption. So as per assumption this is contradictory. This contradictory occurred due to our wrong assumption that root 5 is a rational number. Hence root 5 is a irrational number. So for root 2, root 3 and root 5 same are for all the cases steps are same. Simply you write by replacing 2, 3 and 5. You practice it. It is very important question. Next here, the combination of a rational and irrational number. 3 plus 2 root 5. Prove that this is a irrational number. This is also same thing. 3 plus 2 root 5 is a irrational. First we assume this is a rational and we keep root things in the left hand side and all other things in the right hand side. Okay. So since in the right hand side all other things are integers, we got this is a rational number and root 5 is a irrational number. So on LHS side we have a rational number, on RHS side we have a irrational number. So both cannot be equal. This contradiction arises due to our incorrect assumption that 3 plus 2 root 5 is a rational number. So we conclude that 3 plus 2 root 5 is a irrational number. Here also prove that the following are the irrational numbers: 1 by root 2, 7 root 5 and 6 root 2. For all things same thing. First we assume this thing is a rational number and we write the equation and we take all root parts in the LHS side and all integer parts in the RHS side. Since LHS side is root part which is a irrational number, RHS side we have a integer part which is the rational number. So both it is a contradictory that LHS is a irrational and RHS is a rational. So this contradictory arises due to the fact that we considered the given number is a rational number. Hence we prove that the given number is a irrational number. Okay. See here, for 1 by root 2 also same. 1 by root 2 is equal to a by b, root 2 is equal to b by a. Here root 2 is a rational number and b and a are integer, means b by a is a rational number. On LHS we have irrational and on RHS we have a rational number. This is the contradictory. So we conclude that 1 by root 2 is a irrational number. Same for 7 root 5 also. Everything is same. Same for 6 plus root 2 also. Okay. Like this, first two parts are there. One is root of prime number is a irrational number. One problem is such problem. Next, combination of rational and irrational numbers, that is 1 by root 2, 7 root 5, 6 plus root 2. These are combination of rational and irrational numbers. Okay. For that, first thing what we write, root 2, root 3, root 5, same proof which I have shown in the examples. And for second part, what we do, we take the assumption that given number is a rational number and we keep root parts on the LHS side and integer parts on the RHS side, so that we will get the contradictory results. From that we conclude given assumption is wrong, so given thing is a irrational number. Okay, this is the irrational numbers concept. So far what we have seen, friends, in this chapter we have studied the following points: the fundamental theorem of arithmetic, that is every composite number can be expressed as a factorized or product of prime numbers, and this factorization is unique apart from the order in which the prime factors occur. So order can be changed but the prime numbers are same always. And second theorem what we have seen, if p is a prime and p divides a square, then p divides a also, where a is a positive integer. This theorem also we have seen, and prove that root 2, root 3 are irrational. Okay, these examples and proofs also we have seen. And also we have seen that LHM, HCF and LCM, and HCF into LCM is equal to product of the numbers if two numbers are there. If three numbers are there, then these are the formulas. If three numbers are there, then LCM of PQR is equal to PQR multiplication into HCF by HCF of all numbers. So for calculating LCM, when given HCF, we use this formula: HCF of PQR by HCF of PQ, QR and PR. Similarly, for HCF, we write this formula: PQR multiplied into LCM of PQR by LCM of PQ, LCM of QR, LCM of PR. So if LCM is given, we can calculate HCF. If HCF is given, we can calculate LCM for three numbers like this. Okay, if big numbers are there, then we can go by this method. Okay friends. Okay friends, thank you. Please like and subscribe my video if you like. Thank you friends.